And let's just see how Ian lands his. It might be similar to you. How many people did it Ian's way? Is this good? All right. As I walked around, I think I saw lots of people were doing it your way, Ian. So you follow his work. Is this matching what you have in your paper, maybe? I'm just really curious to see if in the end we get the same answer.
1, 2, 2, not 1.
Yep. So he wrote.
And then, yeah, wait, then you do, so then I do,
So you got ln 2 over 2 also, yeah? Okay, good. All right, and then just by inspection, this one's actually not maybe as hard, maybe, because, well, no, it is a little tricky. I don't know, at least we don't have a definite integral to do, we just find the derivative. So if you, again, maybe two ways to deal with this. You just see, you can either do pre-calc on the front or pre-calc on the back, whatever, you know, but at some point you need to maybe think about log properties at some point. What to do there. I'll take a volunteer who'd be willing to put up the work on this one. Anyone get it yet? And then as we see his work develop, maybe we'll put another solution up that's similar that gives the same result, maybe. We're trying. Try not to hit that button on this one. Both of them.
I do like that.
Anyone have another route to the solution that they want to put up here? If not, it's fine. I just thought there is another way that in the end you might have. It might be worth showing you the other answer just to show you that at first it seems very, very different. If you do it this way, I'll just show you over on the board here too. You might be tempted to do what I did at the beginning too, and that's to write this as ln x over ln 3 cubed over x. So if you did that, you might start by saying, well, that's 1 over ln 3 cubed times the integral of ln x cubed over x dx. So that's ln of ln 3. And then the antiderivative of this is a little easier for me to do in my head now, right? It's just u to the 4th over 4. Right, so I think I did it. Check me on take the derivative if you like. So is that, like in the end, is that an equivalent answer? It's a little harder to tell here that those are equivalent. Can you stop and just make sure that they're the same? Full credit for either answer here. this one or this one. Check that it takes a little bit of work to see that they're the same, maybe. Yeah? This is ln x over ln 3. So that'll be ln x to the 4th. But then there'll also be an ln 3 to the 3rd that we're dividing by here. An ln to the 4th, rather, that we're dividing by there. Or over here, but then there's another ln 3. You see how that's going to work out? They're the same. They are the same. I promise. Anyway, so is one better than the other? No, they're both equally, a little bit equally messy. They're not, either one is pretty. Okay. All right, the only other, well, we have, I was telling someone earlier, we have this project, this ongoing project of trying to reconstruct all the antiderivatives from the derivatives we knew, right? So that's where we're at here. We're trying to do as many things as we possibly can that pull back from what we knew earlier and use properties of logs and undoing the chain rule backwards with the do substitution. Yesterday we did try to find antiderivatives for some trig functions and for some exponential and log stuff and 1 over x. So we're building our collection. The only other one that I might want to add in here, well, we have a couple things to add. One would be, though, is the inverse trig functions. And by that I mean things that when you take their antiderivatives, you get the inverse trig functions, is I guess what we really mean. Namely, these kinds of expressions, right? These are, I don't mind putting them in a box right now, right away. There's no surprise here. They're all exactly the same information that we gave you earlier this year, just run the other way. We said the derivative of arc sine, you showed me you know, or remember, or you had to look it up maybe. In the warm-up, you showed me you knew, is 1 over the square root of 1 minus x squared. Do you remember that? So there's no new information here at all. Okay. But it does go to show that if you see one of these guys, you might not be thinking trig when you first see it. Yeah? So I need you to start being aware of how these are going to look out in the wild, right? I mean, I think if we see something that has trig functions in it, maybe you're like, oh, well, I'm gonna need to pull on my trig now. But if you see something that's the integral of 1 over the square root of 1 minus x squared, you might not be thinking trig right away. And again, there's actually no need for the second set of boxes. Maybe you can see why, right? Because if someone says, well, I need to take the antiderivative of this guy, well then won't this one do? Just with a negative out front? Is that true that sine inverse x of x plus c is the same as negative cosine inverse of x plus possibly a different c? And the answer is yeah, those are just actually, I think we talked about that briefly, at least earlier this year. Sine inverse and cosine inverse are reflections and then translations of one another. If you remember how those looked on the graph, feel free to work that through again. So in fact, as we go, earlier this year, we might have had you said, hey, what's the derivative of cosine inverse of x? And you would have had to think that through and give me this answer maybe. But as we go in the reverse direction, there's really no need to ever, because it's maybe your choice of what antiderivative to give, there's really no need for the second boxes, even though I put them up there, okay? So I might, in the rest of today's lesson, I probably won't reach for those at all, okay? Just so you know. Oh, there we go, I did put that up here. Again, it's just a vertical shift and a reflection. So that's why that happens, remember. All right, armed with that, let's just expose you to a couple problems involving these as we've been doing. Just really practice, right? This is all we've been trying to give you. Throw lots of problems at you until you get good. Hit the gym. Get strong. Okay, having learned not very much except for possibly being reminded of those integrals, let's move on to actually try these. Okay, again, I just want to caution you, in this particular context right now, you're like, oh, these are probably inverse trig functions. But when you see these mixed in with other ones, I don't know that you'll see that right away. So just be careful. Now this first one looks a little bit like what? Now look carefully. Yeah, secant inverse, arcsecant, right? The only difference might be that there's no absolute value. Why isn't there a need for that here? So, yeah. Yeah, the only theta that we're considering in this particular moment of our lives are those positive values of theta. All the values for which we care about, okay, are all positive. So that kind of does make a difference for us. So with that said, there's nothing trick. There's not also any other elements here. Like when we get to something like this, there's obviously some other things going on besides just straight up the. But it's just, what is it? It's arcsecant, right? Theta. And then the work here doesn't lie there. It lies in us actually evaluating this and actually remembering our trig. Right? That's work too. But it's not really trig. It's not really calculus work right now. We just need to think, okay, well, how does this go again? What's the secant inverse of root 2 and the secant inverse of 2 over root 3? Oh, we can figure those out. I don't know. I don't like those maybe, so maybe cosine inverse of 1 over root 2. What's that? And the cosine inverse of root 3 over 2. All right, and then one more thing. Let's keep diving down the grade level. One more thing you don't like, fractions. Okay. All right. Go down to pre-calculus and then down to middle school. Okay. All right, so what is that? Yeah, 45 minus 30 is 15 degrees. There you go. Like I said, no. So even though that was daunting at first, the reason it was daunting was not the calculus, just to be clear. It was all the trig and the fractions. Okay. All right. So does that feel good so far? This one doesn't look like any of those exactly, but which one does it remind you of? Maybe. I don't know. It looks kind of like sine. I mean, it's got that same kind of like square root of 1 minus x, 6 down there. Except, it looks like it, except, what might, already I'm asking you to suggest a u substitution. Except for what? What's the difference? Yeah, if we had what? What would you like to let u be, I guess? Maybe x cubed. Doesn't this feel like it has the form 1 over root 1 minus u squared if u is x cubed? So let's take that and run with it. Oops, sorry. Here, let's actually take a second to rewrite that. There it is. X cubed squared. And already, if you're a veteran user of u substitution by now, you might already be seeing why the x squared there is a huge favor, right? Like that's, oh good, I think I already see all the way through this problem. It's going to work out. I don't have the answer yet, but I know it's going to feel good. So go ahead and once you've made that observation, go ahead and try it. Let u be x cubed. And then work from there. what'd you get? So, did you get, without, I don't know, do you need to see some work there? So du is 3x squared, so that means we have like a 1/3 in there as well. But my first guess is, if I'm just like making wild guesses, is sine inverse of x cubed, right? And then as I look at what I have here, plus c, I also realize that I'm going to need a 1/3, but I think that covers it. Is that what you guys got out there? Okay, so I think I'm good. So do you see how you can do the formal use substitution, and I do recommend that if you're still, but you can also maybe just kind of make a good guess and fix it. Okay, so whatever. So that. Say it one more time, sorry. Provided they're right, yeah. All right. But I mean, slow down and do the whole use substitution if you need to, you know. But I fully acknowledge that, like, if you get used to it, like, you start seeing some of them, right? So do whatever you need to do. Take it real slow if you need to. Take it, you know, go faster. Sometimes it's hard, you know. If your brain is breaking, then write it all out, you know. Which one does this look like, if any? It looks like arcsecant again, doesn't it? So, but there's a little snag there too, isn't there? Yeah, but it's not much of one. But yeah, does this have that form? Yeah, you might rewrite that in there as 2t squared minus 1. So go ahead and do that if you haven't already started into it. Gary, did you get it yet? How are we doing out there? Katie, what'd you get? Katie, what'd you get? Yeah.
Oh yeah, no. Inside, yeah. Oh, I see what you're saying.
I'll see. Yeah, and then yeah, some people, I heard some murmurs about the fact that there's no absolute value there. So how do we handle it? What did you want to say about that? I mean, certainly, do you want to at least tell me when this does seem to work, at the very least? Yeah, if t is greater than 0, we might want to make it even more restrictive than that. T can't be. Yeah, I think you're not allowed to ask about secant of 0 or something. The inverse secant of 0, right? Is that okay? I mean, the domain, I mean, even just think about the original expression even, too. I think it's only defined for numbers greater than 1/2. Or possibly less than 1/2, but then, so we'd have to maybe think about that, too. Yeah, Judah? No, let's not worry about this too much. This is, but I just wanted to assure you that, like, the fact that the absolute value isn't there is, like, still okay, subject to some requirement, but we won't make you say what it is, okay? So don't be too, let's just say this is our answer, but technically, if you really care, there are some technicalities to worry about if you really want to, yeah.
So eventually will we have to put those?
No, I don't think anyone will ask you to get that technical about it. But I just wanted to, I just did want to emphasize that there is like some domain restrictions happening here. We've got square roots, and then we got the secant inverse function, both of which have the same domain restriction. Looking at this, it should be clear that this needs to be true. Looking at this, that should be clear too. That has to be true. Yeah, Jeff.
We're in the 1/2.
Yeah, we're in
It's 2 t's that change.
Yeah, so just, I don't know, just take the derivative of this and you'll feel it, won't you? So the derivative of this is 1 over 2t. Oh, you know what we did miss? There's a 2t here that we need to introduce too, isn't there? So, yeah, we can't just, wait, hold on. We should slow down on that one a little bit. I want to make sure that we did that right, actually. Wait, hold up. So, because if you're actually doing the u substitution, then you need u here and here, don't you? Yeah. So now we can do that, but then let me think about the 1/2. This 1/2, not that 1/2. This 1/2 here. So what do you get then? Does that come out to be? You get the 2 up here. I think. Here, let's take the derivative. Maybe we should actually do the u substitution to see. Well, let's actually take the derivative of secant inverse of 2t. What do we get? 1 over 2t square root of 4t squared minus 1 times 2, which is what we have. So I don't think we need the 1/2, right? We did it too quickly there. Isn't that the original thing? So Josh, you win 1,000 imaginary bonus points. Do you see what we're saying? I mean, isn't this the derivative of that? Without the 1/2, isn't this the derivative of that? And that's this. And you cancel out the 2's. That's this. Yeah.
In the second step, where do you get the 2 on the numerator?
I just decided to multiply the top and bottom by 2, so that we'd have like a u, the same u here as here. Huh? Yeah, if you want to, if you don't want to do that, then you might need to do the following work. Let u equal 2t, then du is equal to 2dt, and then you had a 1/2 du equals dt. But then when you go to rewrite your integral, you'll have 1/2 du. But then what's t? Isn't that u over 2? Right? So then that works out to be, you see the 1/2s go away then, you know, but yeah. All right. This one looks very, very innocent down here. Yeah, we might need to factor out a 9 out of the bottom. How's that going to go? We got a 3 times 1 minus x squared over 9. Is that right?
Yeah.
Yeah? So we have, that's not a cube root, that's a 3 times, sorry. All right, I think that might get us in the clear now. I mean, the problem we started with is this looked really nice and all, but we really like a 1 minus something in there, don't we? So we're really going to great lengths to make that happen. So now letting u be x over 3 seems to be a good choice. And by the way, a 1/3 dx is in fact what we have here, isn't it? So we just have a 1/3 dx is du over the square root of 1 minus u squared. So that gives us sine inverse of u plus c, or sine inverse of x over 3 plus c. But again, that you kind of don't see that coming.
No, I didn't. I was like sitting there, like, yeah. I know. I straight up like I was but I was like, oh, guys, it's just